artificial intelligence will completely transform our world. But what is AI? Why will it affect you? And how can you and your business survive and thrive through the AI revolution? Welcome to AI and You. Here is your host, author, speaker, and futurist, Peter Scott.
Hi, this is episode 194, and today we will conclude the interview with Rachel St. Clair, CEO of Simuli, which she co-founded with Ben Goertzel, who was here in episodes 106 and 107, and who coined the term artificial general intelligence, or AGI, something we spend a lot of time talking about on this show. Rachel is a fellow of the Center for Future Mind, with a doctorate in complex systems and brain sciences from Florida Atlantic University. She researches artificial general intelligence, focusing on complex systems and neuromorphic learning algorithms. Her current work is focused on understanding the neural basis of consciousness and its relationship to learning. Last week, we talked about markers for AGI, distinctions between it and narrow artificial intelligence, self-driving cars, robotics and embodiment, and disco balls. Okay, so the disco ball was Rachel's visual model for how hypervectors represent information in multidimensional space. You'll hear more about that in this part of the interview. Let's get right back into it with Rachel St. Clair. I want to connect this to the power comparison that you're making, because at Simuli you're working on some hardware, I believe, and the way that we implement neural networks at the moment, if you're using classical von Neumann chip design, wastes a whole lot of layers of abstraction, because you're converting these high-level programs that are modeling vast arrays and matrix operations into machine code that executes to manipulate registers of numbers, do addition and multiplication, when the problem itself of all of this matrix multiplication is one that's very well suited to being implemented in hardware itself. And you would take out like 3 orders of magnitude of, I'm guessing, of abstractions being interpreted into the next layer if you did that directly. And one attempt to do that directly is called neuromorphic chip design. So perhaps you can speak to that industry and what you're doing at Simuli.
Yeah. So the advantage of hardware for us is that it makes things faster, because we're dealing with some certain types of Boolean math, just straight binary math. And most of the hardware today that uses this von Neumann architecture, there's 2 things going on. One, you're using floating point math. So we've traded precision and accuracy. There's a little bit of a trade-off there for being able to compute a larger expression, a larger range of expression, which is why we moved into floating point, which is extremely useful. I'm not getting rid of floating point. Floating point is good. But for certain processes of moving vector spaces, if you want to keep your vectors from exploding and getting too big, getting too saturated with numbers, you actually just want to be using zeros and ones. You don't need all these floating points. So redesigning hardware to just use kind of this binary vector space is useful. It makes it faster. We don't use too much matrix multiplication, a little bit here and there, but it's not our core. That's not how our core learning algorithms work. And the biggest thing about the von Neumann architecture is that you separate your memory from your logic. And this is where a lot of the compute time is wasted, because if you think about your brain, your information is stored. I mean, this is debatable, but this is what we're subscribing to in neuroscience right now, is that your information is stored in your synaptic connections and the morphology, kind of the structure of how your brain is set up. And your brain is also able to compute on that structure directly. So in biological organisms, we have the memory, where the information lives, and what moves that information around and changes that information in the same place. So if you want to go find a piece of information and then do something with it, it's in the same spot. You don't have to go fetch the information, fetch from memory, and then move it to the correct logic place, perform the logic, and then put it back, which is how von Neumann architectures do it now. So that fetching and moving moving data, especially when you're talking about hyperdimensional vectors, very large vectors, is very expensive in hardware. Moving these large vectors, even in language models, even in current AI, moving data around is expensive. I mean, think about how much data ChatGPT takes to train, right? Or some of these other Google DeepMind models like Gemini and other things like that, right? They take a lot of data, and you have to move all that data through all the logic pieces in the hardware. If you just put your logic and your memory right next to each other, which is more in line with neuromorphic computing, you save yourself a lot of time, which in hardware, time and power are closely related. So,
Can you quantify that savings?
yeah, of course you can quantify the savings. We're still early in our learning algorithm design and architecture. Hardware is the long-term goal for us. We're leading with software. We think it's important to, before you go and spend millions and millions of dollars building the hardware, to make sure that everything else has been ironed out, making sure all the software is how it needs to be, making sure there's no other chips on the market that could do the job. So we've estimated that the power reduction for using hypervector models is about 3x. So if you're Amazon, you're spending $3 million on your power bill to train ChatGPT for OpenAI, which I think they've switched to on-prem, or, but that's another discussion. But you're now only spending 1 million. So this is significant savings when you're talking about just the training of AI models, which isn't even getting into the inference and stuff like that. And then when you combine that with higher throughput, which is probably a little bit separate, but you get even more savings. So one of the good things about these hypervector models is that they're somewhat holographic, right? So you can stack information on top of itself. So if you're familiar with how holograms are made, and I'm not talking about the really cute little stamps that you get at the post office that are shiny, and when you turn them, they show a different picture. Those are cool too. But real holograms with photolithographic paper, there's some really good old videos on how these work. What you do is you take a wave interference. So you have a light signal, two light sources. And those two light sources, when they hit each other, it's like ripples in a water where the ripples clash. And when those ripples clash, they create an interference pattern. And so instead of saving the original data, you can just take the interference pattern. Just take the interference pattern. And so you can actually get away with using way less data and not keeping all of the original data. And you can use that to train your AI models. You can use that as your source of information. That's how your data lives. It doesn't need to live in the original form. So this is where vector spaces are really important. This is kind of similar to what large language models do, is they change the representation of data to be more compact, to be something that's more manageable to do all these mathematical operations on. And so how your data lives and what it looks like, which is an internal model process, that's before, I'm talking about after pre-processing of data, right? There's also, you have your images, you got to make your images all standardized, pre-processing. I'm talking about after that. How do you get your data in a form for your model to compute as few computations as needed and still get the same accuracy?
Right.
You can do that in regular software, but in hardware, if you embed these computations in this data transformation directly, it just speeds it up so much, because normal computers, they want everything to live in floating point, and they want the memory and logic to live very far away. And you need to get rid of those two things to be fast with this different type of vector math.
Wow, so much to work with there. So many notes. When we're talking about how this makes for smaller power requirements, but also faster, one of the, it seems, limiting aspects of the large language models at the moment is how long the training takes. I think it's still in the weeks, especially if you include the reinforcement learning with human feedback phase in there, whereas human beings learn continuously. So can you see yourself getting to the point where we can have continuous learning in AGI so that there is no independent training phase?
I was kind of hinting at that earlier, so I'm really glad you picked up on that. I think it's necessary. I think it's absolutely necessary to have online learning. We cannot be taking these brains, if you think of these AI models like brains, can't be taking them offline and turning them on. And humans, I'm going to throw a lot at you here, so I do apologize in advance if it's too much. But in humans, we do a lot of our learning during sleep. We do this process called synaptic pruning and growth. And that's basically you have dreams, and these, whether you remember your dreams or not, which if you remember them is actually a wasted use of resources. So don't feel bad if you don't remember your dreams. It's actually more efficient. What you're doing is you're setting up new pipelines for information to travel on. And then the next day when you wake up, if you encounter any of those pipelines being useful, they stay. And the ones that weren't useful, they get tore down and they get put somewhere else. So this is how our brain does resource management, and we don't have to grow new neurons every time we need to learn something new, right? This is one of the ways. So we manage our synapses, we break them down, we put them new places, we make them different shapes, different sizes, and that changes how the information lives in our brains. So this is part of how we're able to do online learning, right? We have these kind of brief update cycles where our brain is still functioning and processing information, but it's doing a big, heavy update. And there's something similar that happens during waking states too, right? And so I think we'll need something like that in AGI, absolutely. We need to have continual learning. You can't just be taking this thing offline that much. Doing a training cycle for weeks and months, completely new data pours in. The information cycles are way too embedded in the processing of AI models, where it's very difficult to get to online learning because there's not this deeper abstract construct that you can try to retain as you're retraining. So when you're retraining, you update all the way down to the lowest levels of perception for the model, which means that you're rewriting things like Gabor filters. And so in humans, we don't rewrite how we perceive colors and edges when we see something new. For like if you see a penguin and you've never seen a penguin before, we just update our concept of what a bird is. We don't update our concept of what it means to have the color black, have the color orange, have the color white, thinking about emperor penguins. We just update our perception of what birds are. That birds can include these things that don't fly very well, and they're kind of this weird oval shape, and they have these flat, weird feet. And so I think that that kind of updating is the difference between what we have in traditional AI right now, where you have to pull the whole model offline, update everything, update all layers, versus this online learning, which says, okay, we're just going to do some resource management and update some deeper concepts. And there is work that people have looked at this, right? People have looked at, okay, how can you do selective updating, not back propagate all the way down, meta learning. Those are really good examples in the literature for anyone who's looking for some resources of how we've started to move in that direction. And there's quite a few models that do what we call one-shot learning. So hypervector models, which is a particular class of these AI vector space learning models. Pinty-Canerva in the 80s came up with this hypervector mathematics. Those are notoriously good at one-shot learning, notoriously good at one-shot learning. And so we've kind of already set up this system to build deeper constructs, have an ability to online learn. The pieces are there. There's still quite a bit of research on how to get all the pieces to play nicely together, right? So I'm not saying we've done it. I'm not saying we've made AGI. We're still far from that. But there is some core learning algorithms, I think, that needs to be introduced to the AI field that can help everyone have more resource efficient models, which will hopefully lead to better models, more intelligence in the models. So the paradigm is no longer throw more data at it, throw more GPUs at it, it'll be smarter. The paradigm is, how do you use your GPUs better? How do you use your models better? How do you form your data in a way that's better for the models to be more intelligent? That's the paradigm shift that we're interested in.
Because we already have enough power and compute. I love how you put that, saying we don't update our model of black and white, we just update our idea of what a bird is. It's very mimetic, it's very quotable. And thank you for getting into sleep, because now you've knocked off one of the other things I'd made a note about to ask. Now, because so much of this is involved with embodiment, I want to ask about how much it might be necessary to develop ways of encoding things that human beings sense, like touch, that I don't think we have precise encodings for. So at the moment, we can do very well with text, because we can turn that into Unicode and we know what that is. And we do very well with images because we can turn those into pixel maps, and then that's just numbers, and we can do the same with audio. If you start talking about sentiment, like sarcasm versus surprise, which I can embed in the same word two different ways, I can say right, or I can say right. on the transcript, those will look the same, but they're not. And similarly, the feeling I get from picking up a hot mug versus a Twinkie are radically different, and yet I'm not aware of any way of encoding those that is anywhere close to as rich as text and images, which may be why we've done so much with text and images and so relatively little with learning how to pick up different types of object. To what extent are we going to have to develop rigorous encodings of things like smells and touch before embodiment starts working?
Yes, exactly. So that is exactly what I'm trying to get at, right? So I'm glad you asked this question. So what we're trying to do is we're trying to strip out rigorous encoding. We're trying to strip this out. This is a kind of two-facet thing, right? Because I said we're going to need to have embodiment. And also I'm trying to say we want to strip out rigorous encoding. So it might seem like I'm saying two different things, but they have a place together, okay? So what we want to do in our vector spaces is use a way of encoding that is universal, some sort of universal encoding, a way that says information is information. So if you look at Shannon information theory and things like that, there's some unit of what it means to be an information, a piece of information. And whether that information is coming from audio, or it's coming from smell, or taste, or touch, or vision, or text, or language, or LiDAR, or whatever you want to strap on to this AGI model, whatever embodiment you want to give it, you need to find a way to have all this information be able to transfer and interact with the different parts of this model's brain. And so Ben Goertzel, his team, True AGI and SingularityNet, they're doing a completely different take on this than we are at Simuli. But I think the concept is there, and the concept is there in OpenAI models as well. You use these large vector spaces, or you use large symbolic graph spaces to say, how can information be uniform? And that is the power and the difference of a lot of the AI models that I think is not so often, I don't want to say it's not so often talked about, but it's all in the technical details, right? It's in the devilish technical details.
But if I could interrupt there, you have to have numbers to put in the vectors. And it's obvious what those are when we're talking about text, because we can reduce them to Unicode characters. And it's obvious what it is with images. But I don't know of an encoding system for smells. Are we going to need sensors that are in some way calibrated in a way that you can pull numeric resolution of smells out of them?
So we do have systems like that. It's some very early AI work. I was working with some wonderful people during my PhD who were just starting to pioneer that field, right? I mean, that is still a really baby field of AI, but they're doing a lot of progress on it. It's really interesting work. What we're saying at Simuli is forget where it came from. All these are just numbers. They're just numbers. And currently, what we have now is a system where whatever data is coming in is recorded in floating point numbers, right? And at Simuli, we're saying, get rid of all that, because now you have to keep track of what type of data it is, where it came from. Is this smell data? Is this that data? How do these numbers relate? How big your vectors need to be? What shape your vectors need to be? Is it a grayscale image? Is it a PNG image? Your data is not uniform anymore. Your data takes different shapes. Is it a matrix with 4 dimensions to it? Is it a vector with 3 numbers? Is it a vector with 30,000 numbers? It's not uniform enough. So we use hypervectors. There's some really fancy abstract math that lets you encode from precision space, this perceptual space, into arbitrary vector space. So now you go from smell, sensory, perception, whatever it is, into this disco ball space I was talking about. So you just make everything into a little mirror. And then you just position that mirror accordingly based on what all the other data, where it was positioned, right? So it's about relationships between data points. Is how you construct your disco ball, if I can use that analogy. And this is a really interesting space. And most of the AI field, when we're talking about how to make training cheaper, how to improve our models, most hardware companies are looking at this, and that's where the race is right now. The race in hardware is mostly, okay, how do we get to 8-bit precision? Can we get down to 4-bit precision? There's some math that says, no, we can't do 4-bit precision. We're trying to do sub 1-bit precision because we use this holographic principle. So what that means, to break it down a little bit more layman's terms, is how many numbers do you need to represent a single piece of information? So this ties into Shannon information theory. How can you do this losslessly? What information can you lose? Because in learning, you don't need the exact direction that a photon hit your eye to know that that's a picture of a cat. You don't need so much data to be able to make an inference or make a behavioral selection on what you need to do. So you have to be smart about what data is considered noise and what data is not noise. And you don't always know that if you're looking at general tasks. If you're looking at a very specific task, it's easier to say, okay, that information doesn't help our model. Like our information is trying to predict which planets might have life on them based off the oxygen content. So we only need data that gives us information about oxygen content. We don't need information about light saturation. We don't need information about how much carbon that we can extract from the minerals on that planet or from the interference or how far away they are, blah, blah, blah. We don't need all this extra data. We just need information about oxygen. But if you're building a general model, you don't know because you're not doing one thing. You don't exactly know what in that data is going to be useful. So you kind of need to save as much of it as you can because you don't know what's going to be noise. You don't know what is going to be useful in a different model or what's going to make your concepts, your information concepts, your model of the world rich enough to switch from task to task. So how do you do that? And a lot of AI models are saying, okay, we'll do these really fancy encoding schemes. We can get down to using just 8 numbers to represent one piece of information. I think that's about as low as we've gotten. I think the folks at Cerebras have put a lot of effort into this 8-bit precision, Hugging Face. Everyone's trying to move towards lower levels of precision because fewer numbers means fewer computations. So when you go to run the training, if you're only using 8 numbers for one piece of information, right, a single number in your vector versus 64, normally machines are 64-bit, 32-bit machines, then you're doing considerably fewer computations, right? So that's one way to accelerate things, and we're trying to get that down to a pseudo-quantum level. So that's where quantum fits in, is that we can actually do this on like a sub-bit level with quantum bits, right?
Wow. The more we talk about here, the more levels open up, and now we're on to quantum, and we only have so much time. I love how you're making some very complex mathematics accessible with imagery like the disco ball. When you were talking about the needing to save data because you never know if it's going to be useful, I flashed on Sherlock Holmes and just how he would use so much data that was available from marks on someone's shoe to how they smelled when they came in the room to put all these things together. It seems like the same kind of value proposition.
Yeah.
I want to go back to some of the higher level terms we were talking about earlier and start with your LinkedIn profile says, quote, "My goal is to help create human-like conscious artificial general intelligence to help humans solve the worst of our problems." And if I can focus on the conscious part there, because it's one of those terms that we have a lot of difficulty with in deciding what it means. And then you were talking earlier also about Alex the African Grey, who was a famous parrot. We have an African Grey, nowhere near as capable as Alex was, who would hold conversations. Alex would have a conversation with his owner, who was a researcher, where she would say, like at the end of the day, okay, I'm going off now. Is there anything else you want for the night? And he would say, no, I'm just going to have some more nuts and that'll be it. And that pretty much captures it. So if we were looking at a scale of consciousness, even though I don't yet have a good idea what that means, it's easy for me to say that a rock isn't conscious, a toad might be, and that Alex is definitely getting up there towards human beings in terms of some level of self-awareness. So to what extent does the conscious part of your goal there come into your work? And do you have benchmarks for being able to tell whether an AI has become conscious?
No, absolutely not. I think there's no way to tell if things are conscious. You know, you get trapped in this very deep philosophical debate there. And I don't particularly want to dive into how do you test whether or not something is conscious.
Right.
But my personal philosophy here and what I'm subscribing to in neuroscience and how I think AGI needs to be made, to have extreme levels of general intelligence like this, you're going to end up with something that has some level of consciousness. And there's a caveat there because there's the parlor trick, there's the magic trick, and then there's the real thing. And to the degree to which it's important that those two things are separate, I'll leave that up to the listener to think about.
And maybe you could distinguish for us what consciousness means to you as distinct from intelligence.
Right. So in the model of the brain, information has this hierarchical structure of where it lives in the brain. And how you use that information and access that information has to do with this process that we call indirect activation. And this theory is from Andrew Coward and the recommendation architecture. He's a really brilliant scientist. He used to work at an offshoot of Bell Labs. Well, amazing work. In that theory, what it says is that as information is selected, it propagates up higher orders of consciousness, and one of the highest being language and speech. So I don't want to get into all the nuances there, but the difference is that the way we're building our AGI, it would, by default, if the recommendation architecture should be conscious, it's not something that we would build, it's an emergent property. Okay. Now, you could build things that look to be AGI. I mean, ChatGPT on certain given days, not every day, may or may not seem. And some people have thought that they are conscious. I don't think they are, but you could convince. I mean, what happens when we can convince the world, 90% of the population that ChatGPT is conscious? Does it really matter if it's conscious or not? And so that was the parlor trick that I meant, that, whether or not that matters, if it's really conscious or it just appears to be conscious, that's, irrelevant. It's my point of view, that's more philosophy. But in our designs for AGI, the way that you would go about constructing information retrieval and having to be self-aware, you would have all the ingredients needed for consciousness to emerge. And we wouldn't do that on purpose. That's just what it would take to get something to the level of our own intelligence. Okay, so I don't think I quite answered your question. What's the difference between intelligence and consciousness? I think they're closely related.
What is the aspect there of AGI that you embed in the word conscious that produces some additional value for you? What are you trying to get out of it that is useful?
It's not that we directly want to make the machines conscious. It's just that this recipe for how to make things generally intelligent, how to store deep concepts and models of the world, and then use those models to do things in the world, will have all the ingredients necessary for consciousness to emerge. And you get this process of indirect activation where the brain that we're talking about, and this happens in human brains, is able to self-select information that it needs to finish and achieve its goals. And so that's a really important part of autonomy, is knowing what you know and using that knowledge appropriately to do what you want to do. And that process involves some sentience, right? It involves some ability of self-awareness. We could debate whether or not it's sentience, but some self-awareness at the very least, to say, okay, this is the information that is missing, that's not activated in my brain right now, that it needs to be activated. So Andrew Coward is a very good example of a very low level form of indirect activation, right? And I'll try to extrapolate that up to a higher level. But basically, when you're a kid, let's go back to the penguin example, right? So you're a kid, you've never seen a penguin before, you go to the zoo, and you see this thing, and there's neurons in your brain which are activated that recognize a beak. They see feathers, they see flappy wing structures. So there's part of the concept bird activated in your brain, spread throughout the different neuronal structures. All it takes is a little push to say that's a bird. So maybe it's a smart kid's seen a lot of birds, and they're able to say, I think that's a bird. And the parent or whoever's there says, that's right, that's a bird. So now those pipelines that were laid there the night before while they were sleeping get fired on, and their concept of bird has now been updated. But let's say this kid hasn't had the opportunity to see a lot of birds, right? They've only seen, a robin, a blue jay outside, maybe. They haven't seen even chickens or something. It's a young kid, maybe 2 or something. I don't know. So they can't quite see it's a bird. They say it's a kitty. And the parent goes, no, not a kitty, that's a bird. So that was a consequence feedback that the child just experienced, which now updates the pathways in a different mechanism that says, hey, that's not a cat, that's a bird. And so what happened, what's missing there, so this is typical reinforcement learning, but what's missing in this process, which is very, very central to, I think, AGI and kind of the basis of what might motivate emergent consciousness. There's a lot of other stuff too, but this is a core part, is that the brain is trying to get to an answer. It has to compute. It's forced to compute. You're forced to do stuff. You're forced to think. When you smell a smell, you're forced to smell it, right? You don't have an option to say, no, thanks, I don't want to, you have to remove yourself from the situation. You have to perform an action in order not to compute or to process information. And so your brain is going to try to self-activate the bird population of neurons. If the smart kid, it self-activated enough neurons to push it to say this is a bird, even though those neurons weren't directly activated by the sensory experience, because this was the first time, right?
Wow.
And so that's a very low-level example, but you can extrapolate that further and further, all the way up to language, right? All the way up to kind of really rich concepts and models of self. And that's where you get into kind of a recipe for something that might have emergent consciousness.
Wow. Do you have children? Have you been through that experience?
No, not personally, but I've been around quite a few, and it is an interesting experience watching them learn. I think it's one of my favorite things being around children, because you kind of get to see, it's kind of similar creating an AGI. It's like creating a new person. So it's nice to watch it unfold in real time, in real life.
An extra dimension to parenting. And thank you for bringing up things there that I was going to raise, because when I was talking about usefulness of AI, I'm thinking about having an agent that can go do things for me in the world. It would need to be generally intelligent. It would need to be some sort of electronic butler. And I imagine that it would need some level of self-awareness to be able to perform that function effectively. And thank you for raising that. So as we start to wrap up a fascinating interview here, perhaps you could tell us more about the near future and goals for Simuli and how we will see them and you showing up in our news feeds in the future, and where to look for that information.
Yeah, it has been a really interesting conversation, and hopefully more to come in the future. So hardware and AGI are longer term goals for Simuli. We're not going to build AGI overnight. And so what we've done is we're focusing on the first part of this. How do you store data? What does data look like? And that encoding piece that you and I talked on for quite a bit. That's where we're starting. And so we're working on some new compression techniques, data agnostic, seemingly lossless compression. I know, not as exciting as AGI, but it also is very important for other parts of tech industry. It's pretty important. How do you store data, and can you get that data back without corrupting your data? So we're very close to releasing, our first kind of MVP, first product here called Nebulae. It's a data agnostic, seemingly lossless compression. And from there, we'll start building up our AGI model called ReArc, named after the recommendation architecture from Andrew Coward, as I said. And we'll start to integrate and build the bridge between the two, right? So we've kind of got this in-structure framework that has these new learning algorithms. And we've got the new things. We got the total end of the spectrum. How do you store data? How do you encode data? And we're building the bridge between the two. And from there, we'll see a lot of, kind of lower level AI programs come out, anomaly detection, recommendation engines, things like that. So we've got a rich product roadmap ahead of us. We got a really great team. And I think my next speaking engagement will actually be with Dr. Ben Goertzel in Panama City for their unconference Beneficial AGI 2024 conference. So I think that's a virtual event. If anyone is looking for some more AGI in their life, that would also be a good place to look. So there should be a lot of exciting new things popping up shortly on the horizon. And thanks again, Peter, for having me.
And thank you, Rachel, very much for coming on AI and You.
Awesome. Thank you.
That's the end of the interview. Some really dense information there about the cutting edge of actual AGI development from one of the people making it happen. In today's news ripped from the headlines about AI, researchers at New York University have created an artificial neural network that outperforms ChatGPT at adapting itself to new language, to use words that it has never encountered before. Its human-like performance suggests that there has been a, quote, breakthrough in the ability to train networks to be systematic, according to Paul Smolensky, a cognitive scientist who specializes in language at Johns Hopkins University in Baltimore, Maryland. And they knew that it hadn't encountered those words before because they gave it words that they made up that had never existed before, and certainly not with the interpretations that they assigned to those words, like associating them with geometric shapes. For example, the phrase dax-fep was shown with 3 red circles and lug-fep with 3 blue circles, indicating that fep denotes an abstract rule to repeat a primitive 3 times. They then tested the ability of people and large language models alike to apply these abstract rules by giving them complex combinations of primitives and functions. They then had to select the correct color and number of circles and place them in the appropriate order. To make the neural net human-like, the authors trained it to reproduce the patterns of errors they observed in humans' test results. When the neural net was then tested on fresh puzzles, its answers corresponded almost exactly to those of the human volunteers, and in some cases exceeded their performance, and that of GPT-4. Melanie Mitchell, a computer and cognitive scientist at the Santa Fe Institute in New Mexico, who was on this show in episodes 142 and 143, says this study is an interesting proof of principle, but it remains to be seen whether this training method can scale up to generalize across a much larger dataset or even to images. Next week, my guest will be Roman Yampolsky, professor of computer science and computer security at the University of Louisville, Kentucky. Our first three-peat guest, here to talk about his new book, AI, Unexplainable, Unpredictable, Uncontrollable. Well, that interview will be unforgettable next week on AI and You. Until then, remember, no matter how much computers learn how to do, it's how we come together as humans that matters.
That's all for this episode of AI and You. Please leave a rating and comment and share with your friends. Get the book Artificial Intelligence and You and see more videos and articles at aiandyou.net. That's aiandyou.net, where you can also send us your questions. Thank you for listening.